Here, it's a great honor to speak at BayPiggies. I'm going to present the two projects that I've worked on during the last year, and the first one is called JET, which is a different take on a JIT than a just-in-time compiler, where we try to accelerate basically NumPy with C++. And the other one is Xtensor, which is a C++ library with data structures for data science. So just some quick words about me. I'm Wolf, and I'm a robotics student at ETH in Zurich. And yeah, as Jeff already mentioned, I'm currently writing my master thesis at the Autonomous Systems Lab in Stanford. And yeah, I'm kind of researching autonomous cars, drones, and other robots things. And yeah, I kind of already said that. But yeah, JET is a Python library, and Xtensor is a C++ library. And one of the key features of Xtensor is that we try to have a API very similar to NumPy. And we offer bindings to R, Julia, and Python, and I'll come back to that later. But I'm going to start with JET, which has a interesting logo. And so one of the big motivations for JET was that it was done at a robotics company with a colleague, and we wanted to accelerate math-heavy code because we had numerical simulations of physical quadrotors, and we kind of observed that when we have NumPy code, oftentimes the data types and the shapes are kind of known. So basically, it's like something which you could take and give to some sort of compiler without having to add any other information than what's already there. And so what we're trying to do is combine the beauty and simplicity of NumPy and the speed of C++11. This slide's empty. And our target audience is basically Python lovers who need speed in numerical systems. And we used it to solve ordinary differential equations and do some optimizations with least squares and simulate large dynamic systems. And so how it works is usually you have NumPy and you have a Python script that calls into NumPy. And NumPy calculates something and returns you whatever the result of that calculation was. So our approach is a bit different. So instead of we emulate the NumPy API code, so we try to have our JET API be exactly the same as NumPy. But instead of directly evaluating to a result, we record all of the operations that are done into a computation graph. We register them there, and then from the computation graph, we generate some C++ code. And the C++ code is then compiled into a shared object by using Clang or GCC or one of those compilers. And this object is loaded dynamically into Python, and you can call the function that was a Python function before directly from Python through means of PyBind 11. And just to show you a short example of how this works, is basically we have three types in JET, which is a placeholder, a variable, and a constant. And a placeholder is basically the input to the function that you're going to generate. A variable is some sort of, so what we're generating is actually a class that has a variable that you can change. And the constant is obviously something that will never change, constant. And then we have overloaded all the operators on these custom types. And so when you do a multiplication, instead of actually performing the multiplication, we record this multiplication in this computation graph, and calculate what kind of shape will result and what the data type of the resulting object will be. And then when you do another operation, like down here with the result of this multiplication, it will just take the result here and create another object in the computation graph. So this is pretty similar to TensorFlow or Theano. So probably most of you have seen that somewhere. And then when you want to like evaluate, so when you want to create this function, you use the output that you got from this operation down here, and then use Jet Builder, basically compile to C++ and then into an object. And what you get is a module with a class, and this class contains, so then you can create an instance of this class, and this class has this variable that you can define as whatever you want. You can set it through this, and call the function which you've named over there with your input and get the result. And all of like this operation is then performed in native C++ and hopefully with native speed. So this is some, like from the example I just showed, that would be the code that's generated. So what we see up here is the constant that we've added. And then this is the class in C++. And the variable as a class member, which is defined with some initial value. And the function down here, which is Armadillo C++ code. And down here is the Python binding code, which is using pybind 11 to define the function and to define the settable variable. So yeah, this kind of makes it very easy to create optimization code in Python that runs fast. And just some quick words about the library itself. The library is quite small, like compared to other libraries that do similar stuff, like TensorFlow, Python or Python. It's only about around 3,000 lines of code, and it's a very like transparent conversion to a C++ class, and not like I don't know, NumPy, for example, compiles to LLVM intermediate representation, which is very hard to read, while the result of Jet is pretty like transparent to use and to read and maybe debug, what hopefully won't be necessary. And yeah, we're not trying to re-implement Python, which other JIT compilers try to do. We focus on just NumPy, just the numeric part. And by compiling to C++, we can basically piggyback on existing linear algebra libraries like Armadillo or hopefully Xtensor in the future, and use the incredible compiler optimizations that are available already. And all of this, like when you use Jet, it's like you only compile optionally, so you can just continue to use NumPy for prototyping, etc. And yeah, if you want to migrate from NumPy, the easiest way is to use the JIT decorator, which is demonstrated down here. So using the JIT decorator, it will, like the first time you call the function, it will replace the arguments that you give the function into the specific Jet objects. And then record the graph through all of these functions, use the return value to create the C++ module, and then you can just call the function as you would normally do. And only the first time you call it, it will be relatively slow, but afterwards it's compiled and should be fast. So we've used this, as I quickly mentioned in the beginning, for quadrotor simulations, where we had basically a full state model with quadrotor dynamics and propeller dynamics and a sensor model and a control system, which we integrated by using SciPy OD_int. And we observed the 55 times speed up of this mass-heavy Python and NumPy code without having to basically change much of the code. And just quick words about the backend. We're using Armadillo currently as the backend for Jet. And Armadillo is like a super cool library, and it's extremely well designed and fast. But the semantics are a bit different from NumPy. So for example, you can't have arrays with n dimensions. You can only have, I think, 3. And it's in column-wise storage and not row-wise like NumPy, and there's no fancy broadcasting that NumPy offers, and some of these things, which we, to some degree, had to emulate in Jet, but to some other degree, it's kind of impossible to use Armadillo in the fashion that we like to. So I came across the Xtensor project, I'm going to talk about later, which hopefully will solve these things in the future. And so, yeah, the outlook for Jet is currently that we would love to soon switch to a NumPy compatible backend like Xtensor, and then we're currently lacking some sort of loop operation. I don't know if you, from TensorFlow, you probably know that they have a while loop. So we'd like to implement basically the same idea. And then we were also thinking about some parallelization feature, because if we have this nice large computation graph, it's kind of easy to find places where you can cut the graph and use subgraphs and evaluate them on different cores. So that would be pretty cool. Yeah, and I'd be happy if you test it and contribute under that URL. And I'm gonna quickly switch over to the presentation about Xtensor. Just the subtitle: Data Structures for Data Science. So Xtensor is like a project that was started by Sylvain Collet and Johan Nabil of Quantstack in July of last year, so it's 1 year old, pretty fresh. And I joined around December. I found the project somewhere on GitHub and started to think about it and committing a bit. But now I'm one of the core contributors to it because I really liked it. And the idea is that the observation was that there are 3 main languages of data science: Julia, Python, and R. And obviously Python is the most important one. And all of those have concepts of ND arrays and data frames, but each of them has slightly different semantics and incompatible in-memory representations. So interoperability between those languages is a bit sparse, but we're all working in the same sort of open source ecosystem. And then there was a workshop in Berkeley in 2015 where the key developers from these communities gathered and they explored data structures across programming languages and basically figured out that there is this issue. And the takeaways were that we'd like to enforce common formats and protocols to communicate and store these data structures and support these protocols across all of the 3 languages. And converge on a common native C++ implementation with bindings for multiple scripting languages. And so basically there's a need for the one tensor to rule them all. Now the question is, what would it look like? And the Xtensor team kind of makes a proposal by saying that the one tensor to rule them all has the requirements that it should be as cool as NumPy and enable the use of data structures from existing tensor libraries. And also, which is very important, is that it should use a transparent system to be able to use large tensors backed by a file system or a database. And so all of these requirements basically say that this one super tensor cannot be just one container implementation. Instead, this has to be some really flexible system, expression system, in which any data structure can be plugged. And the Xtensor, basically Xtensor is the lazy tensor algebra expression system, which I'm gonna talk about now. So what is Xtensor? It's a C++ template library for multi-dimensional array manipulation. And it follows the idioms of the C++ STL. I don't know if you're familiar with that, but it has the iterated pairs and key-value semantics. And then we also have an API very similar to NumPy. And what else is Xtensor? Xtensor also offers Python bindings to enable Xtensor API on NumPy arrays. So it's very easy to use Xtensor through Python. Then we offer the same for Julia and also R. And we also have BLAS bindings. So currently matrix multiplication and QR decomposition and all these fancy operations are implemented through BLAS and LAPACK in the Xtensor BLAS package. And we have SIMD acceleration kernels. And all of this is open source under a BSD license, which is the same license that NumPy uses, and which was very successful, I think, for a lot of these data science projects. And yeah, in case you've ever heard of NumPy, I'll show you a quick comparison between the NumPy syntax and the Xtensor syntax in C++ 14. So just like in NumPy, we have the equivalent of the np.array, which is the X array here, which is templated as a double and some initial values. And then we also have the Xtensor, which is a container with a compile time fixed dimension. So this one has dimension 2. And yeah, you can also reshape just like in NumPy. And then we have like builders for expressions. So you can use linspace or arange or a, just like in NumPy, except for it being lazy, which I will explain in a second. We have views, just like in NumPy. Yeah, which instead of the colon, you unfortunately have to write all. But apart from that, it's quite the same. Then we support broadcasting of expressions and vectorization of functions over an array, and also filter views. And we have reducers. So it's quite easy to just sum over a set of x's or all, or just one axis, or take the mean or product. Then we have operations like where or any, all, and or, logical and or operators. We have mathematical functions like absolute, exponential, cosine, etc. And we have a random initialization of arrays or expressions. You can stack and concatenate. So we clearly copied a lot of the great ideas from NumPy here. But one thing that we have that NumPy doesn't have is lazy evaluation. So instead of evaluating at the time where something is called, we only evaluate if necessary. So when we create this expression here, which is, I don't know, the cosine of some array A and then the sine of B and times C, at this point, nothing is evaluated. It's just an expression. And only as soon as you assign this expression to a container, like here, the expression gets evaluated. And the cool thing about this is that we don't have to create temporaries for all of these sub-expressions. So the usual way to go about it would be to create a temporary for the cosine of A, and then a temporary for the sine of B, and then add both of those, etc. So in the end, you'd have like 5 temporary variables, and basically waste a lot of memory. And we can do that as an optimization through template metaprogramming in the loop that actually accesses the values, and it only accesses each of those values once. Or you can also evaluate basically only at one place. So if you just access one element, and from the result, only this specific element will get evaluated. And so what you can imagine is like having some expression on super large matrices, but you only actually need 2 elements. Then doing this with Xtensor is as cheap as basically writing the code by hand. Yeah, so the result is an expression, and we kind of like through template metaprogramming build this expression tree that you can see here. Yeah, this is what I've just explained is with the temporary variables for each of the sub expressions here, and then adding those, etc. It's like if you just want to evaluate for one specific element, it's a lot of wasted memory, and through using our expression system, basically the index gets like injected into the part of the expression where it's actually necessary, and only gets evaluated at this one point. So a few words about broadcasting. Broadcasting is kind of like one of the really cool features of NumPy, where you can just take like two arrays that don't have exactly the same shape and broadcast this one over this axis, like here. And we support exactly the same operation. And we also support broadcasting like this. You'll only, like, it doesn't create some new in-memory data structure, but it's just also an expression which is only replicating the memory from down over here, and not actually assigning a new array or something like that. And you can also broadcast expressions, and even if you broadcast expressions, they don't get evaluated. So it's a very lazy library. Yeah, for iteration, you can use our xBegin and xend iterators to iterate in a row major fashion. And you can also iterate with a broadcasting shape or with a column major by choosing column major as your layout type here in the iterator template. Or you can also do that while broadcasting. So now as I quickly mentioned before, we also support views, which work pretty much the same as NumPy. So you can create a ranged view with a step of 2, for example. So you get something that selects these elements. And then when you basically assign a value into the view, the value of the underlying array gets changed. And you have the same with selecting an entire row through the all operator. Or you can select some range, and we have this fancy syntax with a underscore placeholder, which will insert the size of the array in the underscore. So it's similar to just using the colon in NumPy, which basically expands to the end of that specific row. Then we also have index views. And with index views, you can select a set of indices, and that will like basically take them out and put them into a row vector. We can also use a filter view, which filters by using a Boolean operation. So this one selects all elements which are bigger than 20. And then you can plus equal assign some value, and 5 will get added to the underlying array at the places where the underlying array is bigger than 20. We also have support for missing values, which is one of the features that Pandas, I think, is championing. So by using the Xtensor optional, you can have optional or missing values. And we support arithmetic operations on those. So if you add those two matrices and one of them has a missing value here, you will have a missing value in the result as well, because it's clearly undefined to add something to a missing value. And then using hash value on that resulting array will give you a false at the place where no value is available. And so how can you get Xtensor today? There are a couple of ways, and one of the most convenient is probably to use Conda. And Conda install Xtensor will give you a fresh installation of Xtensor, but we also have Debian package, and you can use CMake to build your own. And so I'll quickly talk about our language bindings to the major languages of data science. And it's a bit unfortunate that the Python one is the smallest, but obviously it's the most important. So Xtensor makes it very simple to create an extension in C++ for Python through using PyBind 11, which is an awesome library. In case you've never used it, you should try it out. And the way you can create a function with using Xtensor is just use the xt_pyArray as argument here. And then what this one does is calculate the sign of this pyArray, and then use accumulate to calculate the sum of all the values in the array. And then we define the plugin down here. It's basically creating a module called Xtensor Python test, and then define the function sum of signs here, and just giving a function pointer here. And this is enough to basically create a Python function using using Xtensor. And obviously the benefit is that it's hopefully faster than NumPy. And using it from Python is easy as just import NumPy and then import the module that we just built, Xtensor Python test, as XC, and then call the function with some NumPy array, and it will get converted into this pyArray on the fly and insert it into the function, and you can operate on it by using the Xtensor API. And then you can also do vectorized functions, which is pretty cool. So you can just take a scalar function, which takes two scalars as input and calculates the difference between the sine and the cosine. And then use our xt_pyvectorize operator to make it a vectorized function, which will take arrays, so NumPy arrays, and broadcast them over as arguments. So the way you can call it is the same. You create an x and a y here, and then put that in. And as you can see, like, this needs to be broadcasted in some way to work for this function, and all of this happens on the fly. So it's really the simplest way to create a vectorized function. And I don't know if anyone has ever used the C API of NumPy. It's quite tedious. And yeah, using Xtensor, it's a lot simpler. And this, what I just showed, was only for Python, but we basically have the same facilities for Julia and R. So it makes it super easy to create some sort of package or library, and then create bindings to all three major languages and distribute it to all of these users. And we have the Xtensor cookie cutter package, which comes with a few examples from the documentation, unit tests, HTML documentation, and the boilerplate setup.py, or in the Julia case, the build.jl, and basically gives you all you need to be ready to go to build your first Xtensor enabled library or package. And basically, Johan and Silvan wrote a blog post about scientific computing in a polyglot world through the usage of Xtensor. And the main argument is that it's great to write a native extension once and then operate on these Xtensor expressions. And yeah, you get free bindings to R, Julia, and Python. And for more details about the best practices, note down this URL. So what's more, we have as I quickly mentioned before, we have the BLAS bindings. And what we try to achieve with the BLAS bindings is to really recreate the NumPy.linalg interface and have a one-to-one mapping of the NumPy functions to Xtensor functions. And with this, we are kind of seeking adoption by these C++ compilers like Jet, which I mentioned. But we've also been in contact with the author of Python, which some of you might know. It's a JIT library as well, with a large C++ backend. And yeah, we've made sure that the extended BLAS package works with all the BLAS implementations out there. So OpenBLAS, MKL, and Netlib all work, and we test with them continuously. And yeah, the best way to get a feel for what's available is to look at the NumPy to extended cheat sheet, which I can quickly open. So here you can see all the comparison between NumPy and Xtensor. And then down here you'll find the BLAS functions. So we have the broadcasting dot operation, for example, and yeah, Cholesky or SVD decompositions, eigenvalue stuff, norms, inverses, and so on. And then we've also, or basically the work has already completed, but we still need to integrate it into Xtensor as the XSIMD project, which offers a unified high-level API to AVX, SSE, and Neon SIMD operations, and heavily accelerated mathematical functions that basically can compute the stuff like trigonometric functions 6 times as fast as the standard implementations, with a bit of a loss of precision, but not a lot. And yeah, we also have a aligned memory allocator in this package. And we really plan to integrate this SIMD thing into Xtensor to make it one of the fastest libraries on the market. And yeah, this I already mentioned. And then we plan to have bindings to Apache Arrow, HDF5, FITS, and NetCDF, which are data storage formats. And then we're also looking into GPU acceleration a lot, because that's what everybody wants today. And yeah, expressions backed by databases is a big topic. And arrays with labeled dimensions, which is kind of like data frames. And for later, world domination. But it's going to take a while, don't worry. Yeah, so I already mentioned Silvan and Johan. And those two have started the project, as I said, and I joined a bit later. And then Gisline also helped us a lot with packaging everything for Debian and making sure our CMake is, yeah, that's it.
Any questions?
Go back to the first example of the Python bindings.
Sure.
Yeah.
This one?
Yeah, further down, I think. The next page down, I think.
This one?
Yes, I was confused. You say sum of signs and you have this input variable v. Where is v defined?
Oh, wow. It's a bug.
Okay. I was wondering if it was a typo.
It's a typo.
Okay.
Yeah, we can't create variables from nothing yet.
No problem.
Yeah, it's supposed to say A.
Okay.
And then feed that in.
Thank you.
Wow.
Excuse me. How does it find, when you say import Xtensor Python test,
Yes.
does your compiler create a .pyc called Xtensor Python test? How does it actually do the import? How does it know? I assume you're using a regular Python interpreter. How does it know to load? How does it get the Xtensor Python test?
Yeah.
So that's an actual compiled Python module, or it looks like one?
Yeah, it looks like one. So
it just looked like a...
So we're using PyBind 11. You basically, there's this macro here, this PyBind 11 plugin, which does all the magic of creating this module with the correct
So it
semantics
creates
and
a PYC file.
it's a
looks like
SO
Python.
file actually. The shared object thing which comes out of the G++ or so
Oh,
compiler.
okay, but the Python interpreter
The,
can
yeah,
recognize
just
it.
sees that and then.
Okay.
Thank you. I think it's cool that you implemented this in a lazy fashion, but laziness is kind of difficult, I think. So can you talk a little bit about how you do that behind the scene?
So the laziness is implemented through template meta programming. So we have a facility called XExpression. And when you do an operation, you create one of these XExpressions. And the XExpressions basically store references to the underlying arrays and know what kind of expressions they are supposed to do. So as soon as you assign this XExpression or you access one of the values of the XExpression, that's the point where the XExpression is actually going to evaluate whatever it stores and feeds it to the infinitely until you run into some compiler limit. So all of this is basically done in the C++ in the template meta programming stage. But it's an approach that has been, I think, pioneered probably by Blitz++, and Eigen also has this idea, and Armadillo as well. So
you didn't create the lazy evaluation yourself?
I mean, it's part of our expression system, and we implemented it like from scratch in Xtensor. So it's not using any part of Eigen or so, but they have the same ideas with the template meta programming. But I mean, Eigen or Armadillo, they have a lot more legacy kind of. So we've been able to really use the newest C++ 14 features with const expressions and auto and decal type, etc. And those libraries, they date back to like times where template meta programming was much more difficult than it's nowadays. Yes.
Yeah.
Oh, hi. Yeah, looks great. Very impressive. I'm definitely going to check it out. What I'm interested in is the relative performance difference between Xtensor and NumPy, even just doing like a simple matrix multiplication, because NumPy is a lot of it is in C anyway. Yeah. So what kind of performance difference would you see?
So if it's just a simple matrix multiplication, you'll probably not have that much of a performance difference because, as you said, like NumPy basically uses the same C library calls that we are able to use and calls into BLAS functions or LAPAC. So if you have something more difficult, like some expression with more things going on, you'll see that through the lazy evaluation that I've shown, we are actually able to get quite a bit of a speed benefit there. Then as soon as we plug in the SIMD acceleration, we also have quite a bit of a speed benefit by operating on containers and taking sine or cosine and this kind of things. That's bad. Can I turn this off? Yeah. Anyways, so yeah, for simple things, it's not a huge difference. Maybe that's a trick. But for expressions, it's where we gain performance. Right. And obviously, like when you have things like constant folding and like more difficult things that C++ compiler can optimize, which Python cannot, because in Python you have to always basically go back to the interpreter and then ask what kind of object is this. And Python is such a dynamic language that it's very hard to optimize several things, which C++ has been good at optimizing since a while.
Thank you.
Yeah.
Any more questions? Okay, over there.
I'll start while you're walking. At the end, you talked about integrating with like an object database, and I think at the very beginning you mentioned something about, I didn't remember the wording, but it reminded me of NumArray, which had this have an operate on matrices, not all in RAM.
Yeah.
Or at least that's what they're attempting to do. Is that a future thing or something you want
Definitely
done now?
It's not done now, but what's done is that we have this expression system which is super flexible and basically templated on anything. So you just have to provide like some sort of like API that you know from C++, like this bracket operator to access some element. And if you basically template the expression with a database accessor, it could work even today, but we'll be working on this during the next year, and it's, I think, one of the key things that the company that has founded around this project called QuantStack is eager to work on or, got funding for. So that's definitely something that we'll be expecting in the future.
More questions? So I have one. When you were talking about one of your slides, Julie, it was something like a 55 times speed up. Was that was with Jet, I think. So
yeah, that was with Jet.
Was that speed up over NumPy or speed up over kind of using plain Python?
It was speed up over NumPy. Yeah.
Okay. And with Jet, do you expect that you would eventually be able to generate CUDA code or something like that, or would you kind of generate Xtensor code that is going to use the underlying GPU?
That's more my hope, because then I don't have to invest that much time myself.
Okay.
No, I mean, Xtensor is definitely one of the ideas for the future, to have some sort of GPU array, which translate into OpenCL or CUDA, one of those. And I think that's definitely something like we've been kind of like asked to do by the community. So everybody is very keen on doing stuff on the GPU. But generally, like with Jet and this computation graph, you can do quite a few very interesting optimizations by removing expressions that appear twice or so and parallelize some stuff. So I hope I can continue to work on that in the future.
Great. And is there a lot of uptake? Are there projects that are using these today, or is it more?
So Jet was, as I mentioned, quickly developed during an internship of mine at a robotics company, and they are still using it. And Xtensor is, I think, really like taking off now, and we're gaining quite a bit of traction on our Gitter channel. And yeah, I think it's something that is a very nice addition to the ecosystem.
Great.
Because, I mean, from my motivation, when I did Jet, I looked into NumPy and internals quite a bit. And it's it's a lot of C code, which is very specific to Python. And that was, I think, one of my motivations, or one of the cool things about Xtensor is that it's kind of like removed from all of the Python interpreter and the PyObject stuff, and really has this like clean interface to other libraries. Yeah.
Great. Any more questions? Okay, well, thanks a lot. That's great.
Thank you.
And I guess, does anyone have any last minute announcements, anything? And of course, I want to thank LinkedIn for hosting us. And don't forget, next month is going to be at 9:50 mod. So, and I think we have leftover pizza if people want pizza. Thanks.
Thank you.
You have more time to pizza?
I just found out about that.